So we have Physics Ph.D. qualifying exam practice problem number 26, quantum mechanics domain. So let's begin. A particle moves in one-dimensional potential. V of x equals V naught x over a to the fourth with V naught greater than 0. Part A, derive the leading order WKB quantization condition. So this is the WKB approximation for a quartic oscillator. So what we could say here for part A, well, we have V of x equals V naught x over a to the fourth. The classical turning points satisfy E equals V naught x over t over x sub t over a to the fourth, and x sub t equals a times the quantity E over V naught raised to the fourth. And for leading WKB quantization, the WKB quantization is this integral from negative x sub t to x sub t. P of x dx equals the quantity n plus 1/2 pi h bar, where P of x equals the square root of 2m times the quantity E minus V naught x to the fourth over a to the fourth. So 2 times this integral from 0 to x sub t times the square root of 2m times the quantity E minus V naught x to the fourth over a to the fourth dx. That equals, when evaluated, quantity n plus 1/2 times pi times h bar. So if we go ahead and let x equal x sub t y, then dx equals x sub t dy, and V naught x to the fourth over a to the fourth, that equals ey to the fourth. So 2 times the square root of 2me x sub t, 0 to the, and then the integral 0 to 1, square root of 1 minus y to the fourth dy, that is going to equal n plus 1/2 pi h bar. And x sub t equals a times, again, e over V naught to the 1/4. So we could say here 2a times square root of 2m V naught negative 1/4 e to 3/4. And then we have this integral 0 to 1. Square root of 1 minus y to the fourth dy. When evaluated, that comes out to that n plus 1/2 pi h bar. Now from here, we're going to get this e sub n to 3/4. That equals that n plus 1/2 quantity pi h bar V naught 1/4 over 2a square root of 2m times the integral from 0 to 1 of that square root of 1 minus y to the fourth dy. So that is part A. For part B, determine the asymptotic dependence of E sub n for large n. So let's see here for part B. So for large n here, asymptotic spectrum, raise both sides from part A to the 4/3 power. So doing that, you're going to get E sub n is approximately here, this bracket, quantity n plus 1/2 pi h bar V naught 1/4 over 2a square root of 2m times the integral 0 to 1 square root of 1 minus y to the fourth dy, all of that raised to the 4/3. So we could say that the scaling is E sub n is proportional to n to the 4/3. And this differs from the harmonic oscillator, where E sub n is proportional to n. So that's part B. Part C, they want us to compute the first correction to the semi-classical phase arising from next order WKB terms. So for part C, the next order WKB correction, if we write the Bohr-Sommerfeld condition here in schematic form, x sub 1 to x sub 2, p of x dx plus h bar squared I sub 2 of e, that's going to equal quantity n plus 1/2 pi h bar. And that's going to be where our p of x equals square root of 2m times this quantity e minus v of x. And for smooth potentials, the first correction can be written formally in terms of derivatives v of x. And for a quartic oscillator, it changes the spectrum by a relative correction of this order. Change in E sub n over E sub n equals that order of approximation of n to negative 2. So the leading result of E sub n is proportional to n to the 4/3, happens to be unchanged, while the higher order WKB shifts the coefficient at subleading order here for this one. Okay, and now we have letter D. Letter D, they want us to compare the asymptotic spectrum that we got with the harmonic oscillator limit near the origin. Sorry. So comparison with the harmonic oscillator near the origin. For harmonic oscillator near a stable minimum, V of x is approximately 1/2 m omega squared x squared. However, here V of x equals V naught x to the fourth over a to the fourth. So V double prime of 0 equals 0. Sorry. Something caught my throat. Its low energy behavior is governed by a quartic potential, not a quadratic one. The quartic oscillator has no harmonic oscillator limit near x equals 0. And part E, what they want us to do is determine under what conditions the WKB approximation breaks down. So here WKB breakdown. WKB requires the de Broglie wavelength to vary slowly. We have here the absolute value of d dx, 1 over p of x is much less than 1 over h bar. And equivalently, absolute value of h bar p prime of x over p squared of x, that's much less than 1. And it breaks down near, the turning points, x equals plus or minus x of t, where p of x approaches 0, and the WKB must be matched to the Airy function behavior near the turning points. Okay, so that's all for that one, and I apologize for any miscommunication in my voice. Ooh, my voice going. Sorry about that. Thank you, and have a great day.